Welcome to the AP Precalculus course by Mathic Quest. Today we are solving problems based on 1.4 polynomial functions and rates of change. You can download this quick revision sheet from description below. Question 1. Find whether the following are polynomials or not. First, x cubed minus pi x. Here, the power of both variables is a positive integer, so this is a polynomial. Second, 1 over x cubed. Using the laws of exponent, we can write this as x to the power negative 3. Since the power here is a negative integer, therefore this is not a polynomial. Third, x to the power of 9 over x cubed. If we simplify this, we get x to the power 9 minus 3, which is equal to x to the power 6. Since the power is a positive integer, therefore this is a polynomial. Fourth, 8 over root x. Now root x can be written as x to the power 1/2, and if we bring it in the numerator, it changes to 8 times x to the power negative 1/2. So this is definitely not a polynomial. Fifth, x to the power 3 over 2 over root x. Now in the numerator, we have a fraction in power, and in the denominator, it's square root. So at first glance, it might look like it's not a polynomial, but let's try to simplify this. The denominator changes to x to the power 1/2, and using the laws of exponent, we get x to the power 3 over 2 minus 1 over 2. This simplifies to x to the power 2 over 2, which is just x to the power 1. So this is a polynomial. And in the last question, we have x to the power of 7 minus 7 to the power of x. Here, the second term has the variable x as power. That means this is an exponential function instead of a polynomial. Question 2. Find the degree and the leading coefficient of the polynomial. First, 5x cubed plus 3x squared. Here, the highest power of the variable is 3. That means the degree is 3 and the leading coefficient is 5. Second, 3x to the power of 4 minus 5x to the power of 7. Now be careful, the polynomial is not always written in standard form. The highest power here is 7. That means the degree is 7 and the leading coefficient is negative 5. Third, x cubed minus 3 to the power of 5x. Again, be careful of trick questions like this. Here it looks like 5 is the degree, but look at its base. It's not a variable. We only look for the powers of a variable. So here the degree is 3, and the leading coefficient is 1. Fourth, negative 3/4 x squared plus 7/3 x to the power of 6. Here the highest power is 6, so the degree is 6, and the leading coefficient is 7 over 3. Question 3. For a polynomial function f of x, are there any guaranteed extrema for the given values? If yes, state where they occur. First, f of 0 equals 7, f of 2 equals 0, and f of 4 equals 0. Now for these type of questions, always check those values of x where the function is 0. Here, we have a 0 at x equals 2 and at x equals 4. And we know that between two zeros, there is definitely an extrema. So our final answer will be, yes, there is a guaranteed extrema on the interval x greater than 2 and less than 4. In the second sub-question, the function is 0 only at x equals 5. Since we only have one 0, this doesn't guarantee any extrema. Question 4. Is there an absolute maximum or minimum for the following functions? Absolute extrema is just another name for global extrema. Now in the first function, the degree is 6. That means it is an even function. And because the leading coefficient is positive, the graph opens upwards. That means we do have a global minimum here. In the second function, the highest power is 4, so that's even. But the leading coefficient is negative. So this time the graph will open downwards. That means we have a global maximum here. In the third function, the degree is 7. that means we have an odd polynomial. And the leading coefficient is positive, so the graph will be something like this. Since both the arrows are going to infinity, we do not have any global extrema here. Similarly, in the fourth function, the degree is 5 and the leading coefficient is negative, so the graph looks something like this, where again, because of the arrows, we do not get any global extrema. In the fifth function, we have 6 x plus 1 to the power 2 times x plus 2 to the power 3. Now in these type of questions, you can use the distributive property to expand everything. But to save time, we can find the leading term by taking just the highest power variable from each group. Since 6 is in multiplication with everything, we will first take that. Now from the first group, since x plus 1 is raised to 2, so the highest power of x will be 2, and from the second group, we get x cubed. That means the leading term is 6 x to the power 2 plus 3. That's 5. Since this is an odd polynomial, therefore we don't get any global extrema. In the final function, we have negative 3, 2x minus 1 to the power 2 times x plus 3 to the power 4. Let's take the negative 3 first. Now be very careful for this first group. We have 2x minus 1 to the power of 2. So don't just take x squared. This time it will be 2x whole squared. And then from the second group, we get x to the power of 4. Now we have negative 3, 2x whole squared is 4x squared, and x to the power of 4. So that's negative 3 times 4 is 12, and x to the power of 2 plus 4, that's 6. That means this is an even function with negative leading coefficient, so here we get a global maximum. Question 5. Find the following extrema. Alright, let's start with local maximums. Since this is an included endpoint, we will consider it in our list of local maximums. Then we have one here and one here. So these are at x equals 0, x equals 2, and x equals 5. Now among these three, the highest value achieved is 4 at x equals 5. Next we have local minimums, here, here, and because of the included endpoint, here. So that's at x equals 1, x equals 3, and x equals 6. And among all these, the lowest value achieved is negative 1 at x equals 6. In the next graph, we have local maximums here, here, and here. So that's at x equals 1, x equals 3, and x equals 5. Now among these three, the highest value achieved is 4 at x equals 3. And next, the local minimums are here, here, and here. So that's x equals 0, x equals 2, and x equals 4. But now, because we have this arrow going down towards negative infinity, therefore this time there is no global minimum. Question 6. Sketch a polynomial function f of x that has 2 points of inflection, one absolute maximum, and no absolute minimum. First, let's draw a rough sketch of our graph. It says that there is no absolute minimum. That means we can draw something like this. Next, we want 2 points of inflection. That means the graph should change its concavity at these points. So let's erase this middle part, and I'll randomly mark 2 points here and here. Now, till here the graph is concave down. Then at this point of inflection, it changes to concave up, and then again changes to concave down. Our next requirement is one absolute maximum, which we have already got here. Alright, so let's try to replicate this shape on our graph. Okay, so that's how this polynomial function looks. Question 7. sketch a polynomial function g of x that has one local maximum, two absolute minima, and 2 points of inflection. Now here it says one local maximum, but it doesn't say anything about the global maximum, so we will just assume that it doesn't exist. So a rough graph should look something like this. Here's the local maximum, and the 2 points of inflection are achieved here and here, as the graph changes its concavity from concave up to concave down, and then from concave down to concave up. Next, we want two absolute minima. But think about it. Absolute minimum means the lowest value on the entire graph. Then how can there be two lowest values? Well, actually, there is still just one lowest value. The question says 2 because this lowest value is achieved twice at two different values of x. That means these 2 points have the same y value. So if we try to plot it on the graph, then the polynomial function looks something like this, with the two absolute minima here and here.